Let's say that now we would like to consider again our simple system, but instead of putting a DC voltage, we would like a fundamental frequency. To do that, we go back to the harmonic domain file, and we will modify the harmonic spectrum of the input. I am commenting the one that defines the index 0 Fourier coefficients, and I will use this h2i function to define the -1 and +1 harmonic rank Fourier coefficients. I could directly say their value, but instead I use a very convenient function, which is the DSA sign. It gives the Fourier coefficients of a sine wave with magnitude equal to whatever you give as first argument, and with phase angle in degrees, which is what you give as second argument. So just to give an example, if I want a sine wave of magnitude 1 with 0 degrees as phase angle, it gives me directly these two Fourier coefficients, the one related to the -1 Fourier coefficients and the one related to the +1 Fourier coefficient. If I try to run, so now that I have modified the spectrum, I could directly run it with Control Enter in this section. It will give me an error. This is because I am running without having changed the maximum harmonic rank. So I am trying to provide fundamental frequency information while looking for a constant operating point. This, of course, doesn't work. If I want to find harmonic data up to the first harmonic, which is the fundamental, I have to solve up to the first Fourier coefficient. If I rerun, the same lines as before as are written in the command window, I see again that the equation has been solved. I have more unknowns. Specifically, we have two states, and each of them is now described with three Fourier coefficients, -1, 0, and +1 ranks. And I see that all of them have converged to very small values, so I am confident in the result of the collocation method. And naturally, I have access directly to the eigenvalues of the Jacobian. There are no delays, so these eigenvalues give me information about stability. I see that they have the particular structure of frequency lifted systems. To understand why that is so, you can have a look in chapter 5 of my PhD thesis. Again, if I want to access the data, the results, I can directly go to harmonic domain. It is still the same structure. I find that now the input and state variables are not just a 1-by-1 number, but a vector of 3 elements, which makes sense since there are 3 Fourier coefficients. The input is exactly what we have defined earlier, a fundamental frequency sine wave with 0.5 volts or 0.5 per unit as magnitude. So what can be interesting to do now is not just to have a look at the spectrum, but also at the waveforms. So just before doing this, I can have a look at the harmonic spectrum of the inductor current and the harmonic spectrum of the capacitor voltage. I have written a function called DSAplot, which actually resamples all of these harmonic spectra and plots them. You can also visualize the harmonic spectra by means of this function. If we look at this first part, we see that the code suggests to run this code snippet to get the list of all available variables. So if I do Control Enter, it displays the list of all the variables that can potentially be plotted. I copy-paste this and replace the previous set of variables, which is just another system on which I was working earlier. I can uncomment this, and I have twice the IL current because it is defined once as a state variable and once as an output. So in the meantime, I can just delete it, and I have my two states and one input variable. There are a number of things you can do with this plot file. First, I would like to observe the harmonic spectra. So I am considering the HD sources. Those ones are related to time domain simulations. I will get back to those after having done a time domain simulation. In the meantime, since I have run the collocation method, I have access to this this harmonic domain source. The second entry is just a legend name, but it could be anything. If I run this part of the code, I have three harmonic spectra, one for the input, one for the capacitor voltage, and one for the inductor current. And I see indeed at the -1 and +1 Hertz, the peaks related to the fundamental frequency waveforms. So these results are not very impressive because we're working with only one frequency and with no constant parts. But for a more elaborate harmonic spectra of input variables, these plots will be populated with more harmonic components. In any case, I can also visualize the time domain waveforms, and this is what I can do by uncommenting a line in the time domain sources. If I uncomment this one, then I have access to this structure called time domain collocation method covering one fundamental period. If I go to the DSA structure, the time domain results, this is indeed the results of the collocation with the collocation method written as time domain waveforms. I look inside, have one vector for time, and I see a number of sample points, and all of the variables have their sample points as vectors as well. I can, for instance, have a look at the first 10 elements of vector IL. Here I have more information. It looked constant because I didn't have a sufficient number of digits, but actually we see that these values are not constant, so you can actually observe them in a time domain plot. So this is what happens if I do this. So I have run this part of the code and obtained this plot. I see that I have one waveform for the current and waveforms for the capacitor voltage and the source voltage. I can also plot them separately. This is the advantage of defining sets. If I want to plot them all separately, then I can define several sets of variables. I can rerun this part of the code, and then I have three different plots for each of the variables of interest. Let me emphasize one thing, is that you always have access to all the options, as well as all of the results after running either a collocation calculation or a time domain simulation. Let's say now that I would like to have the results when I have more elaborate harmonic spectra for the input variables, when we have both a constant component and a fundamental frequency component. So now I have defined the -1 and +1 Fourier coefficients, as well as the zero, the index 0 Fourier coefficients. If I go back to the main file, I rerun again the collocation methods. It gives me the results, shows that everything has converged within a very small error. The equation is solved. I can go back to the plot and ask again the results. I can check the harmonic spectra. And now we have a difference with respect to the previous case where we're solving only for the fundamental frequency. Naturally, in steady state, there is no component, there is no constant component for the current, but there is a constant component for the voltages, as well as the fundamental frequency components. Quickly going back to the contents of the collocation method options, I have talked about the type of Jacobian, which can be either numerical or analytical. If you want to switch to an analytical Jacobian, then you'll have to reset at least once to create it. By default, the calculation of the eigenvalues of the Jacobian is set to 1. There are additional vectors and values that are provided, in particular the sampling time and the sampling frequency related to the sample time vectors used in the collocation method. At the very last iteration, the numerical value of the Jacobian is also provided and then stored in the DSA COLL structure. The eigenvalues that are displayed are the eigenvalues of this matrix.